Okay, so today's lecture is kind of continuing on the concept of image segmentation, okay? And the specific thing we're going to talk about today is called snakes, also known as active contours. At the end, we'll talk about briefly what are called level sets. And so the philosophy behind this material is that everything we've talked about so far in terms of segmentation has really been at the pixel by pixel level, right? We threshold and we get a set of pixels, right? Or we do graph cut, we get a set of pixels, right? But as humans, our natural inclination is more about kind of like, if I told you to isolate something in an image, you probably wouldn't click on pixel by pixel. You'd probably draw like a freehand contour around the object, right? You think about things in terms of shapes, right? And so that's the philosophy today, is instead of talking about like pixel level segmentation, we're going to talk about kind of curve level segmentation. And the curve is going to be the key concept that we kind of talk about today. And so, the idea is to segment using kind of curves, not pixels. And so to whet your appetite, let's just kind of do an example to show where we're going, right? So again, I'm going to use this same app that I used before in the last lecture, this image segmenter in MATLAB, which I think is in most recent versions of MATLAB. So I'm going to load up an image, and let's suppose that I'm going to use this guy. And actually, before I do this, I guess maybe, because this is a color image, maybe I should RGB degrade this first, actually. So I feel like the option that I want is not there. Okay, so let's go back to my guy here. So this image segmenter, I can, whoops, what's happening here? I can load stuff from the workspace instead of loading it from a file, which is kind of nice. Okay, actually this looks exactly the same. Maybe I could have done it before, sorry. Okay, so what I'm going to do is, first I'm going to draw freehand to say, okay, this is kind of like what I want to outline, my hand, right? All right, now, where's my segmenter here? Here we go. I just had to open the window a little bit more. Okay, so then I'm going to select what's called active contours. And I'm just going to, don't worry about the magic numbers here for the moment. I'm just going to see what happens. Let's just set this to be 300. And I'm going to evolve. And what you're going to see is that this kind of freehand curve that I drew is shrinking inwards towards the boundaries of my hand, and eventually, as it goes on and on, it's going to kind of snap around the contours, kind of like a rubber band, except the rubber band is going inside the nooks and crannies, so it's not just like a convex shape, it's actually going all the way inside, right? So the question is, how does this work, right? How is this contour drawn to the edges of my hand, and how is it finished doing that? So that's what we're going to talk about today, but I just wanted to give you a little bit of a flavor of what we're doing before I go into the math of how it works, right? The math is a little bit more complicated. That's what we're going to talk about most of the lecture. You can see that here it's an iterative process, and eventually, I guess I don't know if I had enough iterations, it's going to crawl all the way inside my fingers and do a good job. It has to take, so this is where it stops. If I had gone maybe 50 more iterations, it would have gone that way, right? So this is called a snake because it basically is like this kind of closed contour that slithers inwards towards the stuff that it wants. Okay, so this is where we're going, but what does this mean? How does it get there, right? So if I go back to my notes, kind of the idea is we want a segmentation curve that, the most important thing is, number one, it conforms to image edges. But at the same time, I also don't want this snake to be too, jaggedy, too pixelated, right? So another kind of thing is that we want, something that's kind of a smoothly varying curve versus, I guess I'd say, lots of jagged nooks and crannies, to use a technical term. Right? So kind of like the idea is that there's this tension between wanting to really go tightly around the edges, but also not wanting the curve to be like, super jaggedy pixelated, right? I want to have this kind of like nice rubber bandy thing. And of course, there's a trade-off between these two things, as I'll talk about in lecture here. And so the idea, which you kind of saw in the MATLAB demo, is that, to kind of draw this in a very sketchy way. So here's my hand. So first, the user draws, I should maybe close this up. The user draws some sort of an initial contour, and then iteration by iteration, the snake kind of, conforms to the object of interest until eventually it snaps kind of tightly around the object. So this is definitely a iterative process, and the idea is that either I set the number of iterations that I'm willing to go this far, or I basically keep the snake going until it doesn't move anymore, okay? So basically we need to kind of specify, to make this work, what do we consider to be a good curve, right? We need a cost function that tells us how good a curve is, okay? And so first of all, we have to talk about how do we describe a curve, okay? So first I'm going to talk about what are called snakes, okay? So snakes, this kind of came into vogue maybe in the late 80s, early 90s, again, probably before many of you were born, but still, at the time, it was like a pretty exciting idea. As a young child, I was, no. Okay, anyway, so basically, a snake are basically what I call a parametric representation of a curve. So, for example, what I mean by that is that I have a function of x and a function of y, and a parameter, s, that goes between 0 and 1 continuously, right? And the idea is that as we change s smoothly, I trace out a closed contour in the plane, okay? So, for example, let's look at how we would make a circle, right? So, for example, I could say something like the x-coordinate and the y-coordinate are r cosine 2 pi s, r sine 2 pi s. S going from 0 to 1. And if I think about what that traces out, so when s equals 0, I'm at r times cosine 0 is 1, so that's r, and r sine 0 is 0, right? So this is like s equals 0. Now as I go around the circle, right, so for example, s equals a quarter says that I'm at pi over 2, right? So this is going to be s equals a quarter, s equals a half, s equals 3/4, and by the time I get back to s equals 1, I'm back over here. And so the curve that I trace out is this nice circle. Pretty circular. And so this is a lot cleaner a representation than if I had to do this in like plot y as a function of x, right? So this is kind of a nicer way to think about things versus something like, if I wanted to represent this like a Cartesian thing, I'd have to do it like this, and I have two functions that I have to piece together to make the whole shape, right? So this is like a nice way of doing things. And you can imagine that this also allows me to kind of trace out an arbitrary closed curve that might otherwise be a huge pain to represent with Cartesian coordinates, right? So you can imagine a curve that I could kind of go like this, and as s is changing, I can kind of go around and around as long as it comes back to the place it started. That's something that would be a freak show to try to represent like y as a function of x. I'd have all these pieces, right? So with S just ranging from 0 to 1, I trace out my curve, okay? So this is the way we're going to represent our closed curves today, okay? And I am going to assume that everything that we're going to do is a closed contour. It is possible to have kind of like an open contour, like an arc, that is conforming to the edge of some object. But conventionally, when we think about the snake stuff, we think about this as a closed curve. All right, so any questions about the setup so far? Okay, so now also the other thing I'm going to say is that really we're going to assume that everything here is in continuous time and continuous space, right? So as I change S, I am moving this contour around. I'm also going to assume that the X and Y values are continuous values, right? So forget about the pixel grid for the moment. I'm going to assume everything is nice and continuous, right? And I will talk a little bit briefly about what happens when you have pixels and so on. But for the moment, it's much, much easier to do a theory when everything is just like, you know, continuous time. Okay, so what I want to do is I want to define what's called an energy for this curve, right? And then I'm going to try to evolve the curve, drive the curve to have minimum energy, okay? And this energy intuitively should reflect how good is the snake for a given image, right? So let's talk about this. So now we want to define an energy function. So let's call that E of C. So C is my curve, E is an energy, that matches our intuition about what a good curve is. And then what's going to happen is that the curve will iteratively evolve, and every step is going to reduce and hopefully minimize this energy function. So again, kind of like what you might imagine that so suppose I've got a convex object. It's kind of like what you might imagine that a rubber band would do if I kind of stretched it around the object and I let it go and you saw this rubber band snap to the contour. It's like that, except it takes a lot more time than the rubber band actually would, right? So what I'm going to do is I'm going to decompose this energy in two parts, okay? I'm going to say the energy function has what's called an internal part and an external part. So the internal part is something that only depends on the shape, right? So this depends only on the shape of the curve. So the idea is that independent of the image, just how nice is this curve, right? And this is going to encapsulate our idea that curves should not be too squiggly, too wiggly, right? So this is kind of saying how good is a curve in general, okay? And then I balance that out with a function that depends on the image intensities. For example, the edges in the image, right? So here I'm trading off how good is the curve on its own and how well does it fit with the image edges. And as you can imagine, there's kind of a parameter that I can use to say which one do I think is more important. Okay. Okay. So now I'm going to talk about what makes a kind of a good curve from each of these perspectives. Okay. So let's talk about the internal one first, the one that just depends on the shape. Okay. So all things being equal, so let's talk about E internal. So all things being equal, I kind of want a shape that is more like this than a shape that is like this, right? So something that is nicely smooth and varying and doesn't have lots of ins and outs, okay? And so if you think about this like a rubber band again, the idea is that we want shapes that kind of minimize the energy of the curve, like how much energy is required to keep the curve in that state, right? So again, think about, you know, your rubber band is just sitting on your desk. It takes 0 energy to just stay there and it has like a nice round shape. Now you try to squeeze it into some sort of weirdo shape. It's going to be like super stretched and there's going to be a lot of tension and it takes a lot of energy to maintain that tension, right? This is like the super hand-wavy way of thinking about it, right? So you kind of want to think about, you know, relaxed shapes have lower energy and, you know, bendy, twisty shapes have more energy. So I want to kind of make sure that all things be equal, I have low energy, okay? So those of you that are more physics inclined than I am can think about this in terms of actual tension, right? Actual energy, right? I'm not a physics guy, but basically it maps exactly onto the concept of how much energy there is inside a physical object. Like imagine that you've got like a metal hoop that's very flexible that you could, you know, suppose you've got like, you know, pegs on a board and you've got this bendy metal hoop and you're either, you could thread the metal hoop around the pegs that would like have this kind of internal tension, or you just put it down on the table and it would have very low energy, right? So again, you could compute all that stuff from a physics perspective, but here we're kind of thinking about from like a math perspective. So we kind of, you know, like the idea, or actually since this is energy, I kind of want to get the sense that this should have lower energy than that, right? And so how do I encapsulate this mathematically, okay? So this kind of idea, let's just say this is encapsulated by an energy like. So let me write this down first, and then I'll talk about what each of the terms means. What integral? Okay. So what do these terms mean, right? So these both, again, have like kind of physics-based interpretations, but my hand-wavy interpretation is that, you know, this term here kind of refers to how stretchy the curve is, right? How, you know, how much pressure, how much tension that curve is under. And so this is kind of related to, if you're a physicist, the elastic energy of the curve. So let's just say here that, you know, a low value of the derivative means this is not too stretchy. Basically, this kind of keeps points on the curve together as a function of s, right? What that means is that as I travel around the curve, going from like s equals 0, s equals 0.05, 0.1, and so on, I don't want the distribution of those points around the curve to be too non-uniform, right? In some sense, ideally, I kind of want to be taking an equal step in arc length of the curve for every little increment of s that I go. So I don't want the points on the curve to be bunched up like, you know, this, right? As I take uniform steps in s, I don't want to have to be like having a bunch of points that are close together and then a bunch of points that are far apart. That kind of means that the curve is, that kind of means that as I move my dot along the curve, that it's traveling at perhaps wildly different speeds, right? And we know the derivative is going to relate to the speed, right? So that's the very hand-wavy way of thinking about this. This part is basically saying that if I want a low double derivative, what that means is that the curve is not too bendy. This is really technical. Meaning that having a term like this basically keeps points on the curve from kind of oscillating. And that's going to kind of prevent me from being in this state, right? So the double derivative of the curve is kind of related to basically the curvature, right? Meaning, you know, at every point instantaneously, I can think about what is the kind of, so again, curvature is a concept that you probably have not come across in calculus, but if you took like a differential geometry course, you know about curvature. Basically, the idea is like, you know, what is the radius of the circle that sits adjacent to the curve, right? And so that could be negative or positive, depending on whether I'm inside or outside the curve. You can imagine that, in a curve like this, as I roll this little circle around the curve, it's changing radius to match the nooks and crannies of my shape, right? Whereas here, I can imagine that I have basically very little change as I roll this circle around the interior of the curve because there's not a lot of little, inlets and islands for this curve to have to negotiate, right? So this basically is our intuition that I don't want to have lots of squiggles in my curve, right? So I think that's good enough for this intuition, right? So basically, this says not too stretchy, this says not too bendy, okay? And, both of these terms are important because, just the shape by itself doesn't necessarily tell me, for example, where the point is along the curve. I could have different parameterizations of the curve that, trace out the same path, but go along that path at different speeds, right? So I kind of have to know not only what is the actual shape that I get, which is related to the curvature, but also I also have to know how fast the point is going around, as a function of s, okay? All right, so all this is just to say, this is my intuition for well-behaved curves. So let me pause and ask, any questions about this? Okay, that's the hard part. The easier part is what makes the curve conform what? Question? No? Okay. No, all right, you're good, okay. Sidebar? Okay, so now the next question is what makes the curve good externally, right? So now we need to kind of make the curve fit with image edges, okay? Well, okay, I guess I gave away the show, right? So what makes the curve good for segmenting an image? Well, I have this notion that the final curve should basically lie right on top of strong edges in the image, right? So in some sense, here's an obvious choice for that. Let me write this down first, and let's talk about why this is good. So now the image finally comes into play. And let me write this a little bit more explicitly. So here what I've got is I've got my image, which I'm going to assume is grayscale. And then at every point along the curve S, that corresponds to a point x, y in the plane. And then I evaluate the image gradient at that point. And I integrate around the curve, adding up all those gradients, right? So let me be a little bit more explicit to say this is like the integral. Let's write down what exactly this number is. This would be saying I take the x derivative at the point x of s, y of s, and then I guess I square that. And then this is basically like the gradient magnitude at each point on the curve. And then I integrate that number as I go around the curve. And I have a negative here, right? So let's think about what this means. So the intuition here is that I want this energy to be really low when I've got edges, right? So let's suppose that there's no edge at a given point, right? That means that the gradient is 0. We know that from before. And that means that at that point, this number inside, let's call this, f of s, this number will be 0, right? So when I get, when I'm in the middle of some flat region, nothing's happening, right? If I have a big edge, then my gradient magnitude is going to be big, and then this number here is going to be some, big negative number, which means that that edge is going to make the cost function overall have lower energy, right? So again, I was a little bit, well, I didn't lie to you, but basically, this energy can be negative, right? And here you can see that it's got to be negative because either it's 0 when nothing is happening, or when I have edges, it just gets pulled more and more negative, right? So overall, if I take the internal energy plus the external energy, I could get some negative number. So it's okay. That's no big deal. But just to know that the energy is not like non-negative, it's actually going quite negative, okay? But this is the kind of intuition, is that I want the snake to be attracted to edges, okay? Okay, so pause and ask. Any questions about this? Does this make sense? All right. So, as we're going to see in just a couple minutes, there are better ways of thinking about this. Okay, so I'm going to show that actually this is kind of like, while a good idea, it doesn't always work so well in practice. We'll talk about why that is. But let me talk now about, okay, so let's come back to my cost function, right? My cost function is basically saying, okay, I've told you something about this, I've told you something about that. Now I need to minimize this, right? That's the whole point, is that every step I want to make that number smaller. So now the next question is, so now how to minimize this. Whoops. Well, this is something that is probably, no offense, beyond most of you at the moment, right? Because this requires a little bit of what's called variational calculus, right? So you guys are used to kind of like measuring, you go on differentiate a function, set it equals 0. That's the way I minimize with respect to that parameter, right? That's how I find the x minimum that does something, right? So that is no sweat. And you can do that in calculus. You can do that in multiple dimensions. But this is a little bit different, right? This is like minimizing a function of a whole curve all at once, right? So that's something that probably you've never done before, right? And if you look in the book, in Gonzalez and Woods, there's a whole chapter that, I'd say that 50 pages of that chapter are taken up with the details of how exactly you do this minimization, right? So important stuff, good stuff, but this is like a one lecture overview. I'm not going to go into the details of this. What I will say is some high points, right? So let's just say, first of all, it requires what's called variational calculus. So if you were a math major, you might know something about this. But ultimately, the other thing is that obviously to make this work for the real world with digital images, we have to kind of get out of the mathy world and come down to the pixelated world, right? So let me just say a few words about how this works in practice, right? So in practice, for digital images, we basically solve the problem by creating a curve C of two parameters, S and T, where S and T are both discrete. So the S part is basically the amount that I'm traveling along the curve, right? So for example, let's suppose I've got my initial curve. This is what my human drew. So maybe this is, the curve at S equals 0. And this is the curve at, This is the curve at S equals 1. And this is the curve at S equals 2, ... So all I'm doing basically is I'm approximating the curve by a set of points around the contour. And let's say I've got, k minus 1 points, okay? Right, so these are now going to be an ordered set of points, xi, yi, in the plane, okay? Which could also be, actual pixel values, although I think that even in implementations, you're going to leave these to be continuous numbers, right? But the idea is that, instead of having this curve, I'm instead approximating the curve by a set of connect the dots line segments, right? And obviously, the more, the higher k is, the more smooth and fluid that curve can be, right? So if k is like 10, you're stuck with basically a 10-sided polygon trying to crunch around your image. If k is like 100, maybe you don't even notice that there's little line segments connecting the dots, right? So we have to make the problem discrete in that way, okay? And then the t part is basically this temporal evolution of the curve. Remember in the very first demo, you saw that I had an elastic shape that was step by step, click by click, matching the shape of my hand, right? So here, basically then, we step this curve as a function of, say I've got this, then I step my curve to the next time step by, and this is very hand wavy, taking a step along the gradient of E, right? Something like, how do I do numerical differentiation, right? So any of you who have taken like kind of an optimization course and you're talking about how do you actually, how does MATLAB actually minimize a function? Well, I look at the point that I'm at, I look at where the gradient is, the gradient points in the direction of the greatest amount of change, and I take a little step along the gradient, then I look where I am, I take another step, that's called gradient descent, right? And so that's like the standard way that you do numerical optimization. And the same idea here, right? Except instead of taking a step in a, in one dimension, I'm taking a step in here. One way to think about this is that now I've kind of parameterized the problem by k 2D locations, right? So there's actually kind of like, you can imagine a big 2k by 1 vector is defining the curve shape at every point in time, and that makes life a little bit easier. You can imagine that now I'm going to take a derivative in this 2k dimensional world, and that's actually the way that it happens under the hood. But I'm not going to talk about this too much. Let me just say this directly, which is that, in practice, this results in a kind of like 2k by 2k linear system solved at each step, at each iteration. And this linear system, this big block of numbers, has to do with a bunch of x and y derivatives in multiple directions for multiple points. And as you can imagine, I've already got in the internal force, I've already got like first and second derivatives just to measure the energy function. If I'm going to take a derivative of that, then I'm actually going to have like third and fourth derivatives. It gets to be like very messy. At least you have to do some bookkeeping to keep track of what the actual values are. But if you're interested, the details are in the book. And so, this is just basically a bunch of finite differences. Let's just say that. And then the result is that the curve will kind of, inch along until the points around the boundary stop changing. And let me just say that if you're going to do this yourself, there is a lot of bookkeeping to do, by which I mean, for example, lots of bookkeeping behind the scenes. Just to give you one example, kind of what I mean by that is that, suppose that I have a curve at time t minus 1, and as a function of s, I find that my points around this curve are kind of non-uniform, right? So maybe what I want to do before going to the next step is to, actually maybe better if I just use a different color here, if I can find my colored pencil. So maybe what would be better would be to say, okay, before I go on to the next iteration, I'm going to resample these points to be equally spaced along the perimeter, right? So that my curve is ultimately more well-behaved. So you can imagine I could, do things like I could change the spacing of the points. I could even maybe change on the fly the number of points. Like if I discover that, I could add some points in regions that I found had high curvature to kind of force the curve to go a little bit further in. So there's lots of stuff that happens under the hood to make a good curve evolution algorithm work, right? When you're living in the continuous time world, you don't have to worry about any of this stuff, right? But when you're living in MATLAB world, you have to worry about this kind of thing. And so I would put this under the category of kind of important but tedious, okay? So let's take a look at how this works, okay? So now I have to remember what my commands are here. Let's see here. Do I have an Explorer window open? Yeah. No, not you. What was the, yeah, I want a File Explorer. File Explorer. No, go away. Ah, I closed the wrong one. Good stuff. All right, try this again. Okay, so I guess I have a function called, or a thing called basic snake. So let's try this. And this is something that I found on the MATLAB, what do you call it? So let's give credit where credit is due. So if I search for MATLAB snake, no, not snake game, right? So here, this is the function that I'm just showing you here, MATLAB Central File Exchange, okay? So just to give credit. And so let's do this. So this is going to be like very simple outline of something. So here, all I'm going to do is I'm going to draw some initial points around the boundary. And then I'm going to start my snake evolving. And, bip, 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 hey, come on, red point, come on. And eventually, this thing will snap around the circle, like so, right? And it took me, it's still kind of adjusting minorly. It took me 133 iterations to do that. And you can see there's a whole bunch of parameters here, like, you know, gradient weight, which is kind of like the elasticity, curvature weight, which is kind of like, I guess I'm assuming that, let's see, I'm sorry, continuity weight, curvature weight, gradient weight are like the three weights on the terms of the snake, right? There are two internal terms and one external term has to do with the edge. And by tuning those numbers, I could probably get, you know, more attention paid to the edges or less attention paid to the edges, right? And there's a bunch of other parameters. So, yeah, it looks great, right? So this, of course, is like a super simple example, right? But, well, okay, let's also try what would happen if I started from inside the snake, or inside the circle. Oh, not so good. My thing disappears, right? So that's not so great. What happens if I were to do something like this, where I'm a little bit off from, here. So here, you know, I'm kind of doing okay. And actually, this is okay. Well, okay, I guess I never really get this guy to slide over to the edge of the circle, right? And so, and certainly if I started like, you know, entirely outside of the shape, then it never finds it, right? So basic idea is sound, right? So lest we forget how well it worked the first time, let's just look at this. You know, this is like the best case, right? So, you know, it does work, right? But it doesn't work all the time, right? And of course, we want something that's going to be more robust. And of course, in real digital image processing, the shapes that we want to segment are a lot more complicated than this, right? Definitely not black and white. So what's going wrong here? Okay, and actually before we start, let's just try, okay, what would we do with a real image? So let's go to, let's see, where did I put that? Okay, maybe I have to close out of here, try this again. How about this one that I showed earlier? So let's draw some points around this guy. Not so great, right? This is where it ends up. So again, and this shouldn't be too much of a problem, right? Because I got such strong edges between my hand and the black book that, I mean, why is it having such a problem? So problem is that the image gradient part is not strong enough to pull the snake in, right? So if I think about it, if I go back to my, notes, right? The external part here is basically just saying, you know, if I am right on top of a really strong edge, then life is good, right? But, you know, what's the problem? The problem is that suppose that I kind of have a situation like this, which is kind of like what I had before. So I've got a say, a dark shape on a light background, and I initialize my points like this, like I kind of did in that example, well, what's happening, right? Gradient here is great, right? Everything is going to basically be kind of pulling, things into the boundary right when I'm right near the edge. But out here in the middle of nowhere, the gradient is 0, right? I'm in a flat region, and there's 0 gradient, and so the snake is not inclined to do anything, right? At most, what you saw in that example was that the snake is kind of forced to contract, right? So the natural inclination in the absence of any image edges is to minimize the internal energy, right? So the internal energy is basically saying, hey, I want you to make this as small as possible. If there are no gradients anywhere, then all I'm doing is minimizing this. And the effect of that is going to be basically pulling the nodes closer and closer together until, as you saw in some cases, the curve just vanishes, right? Then everything is great. Everything is in one place, and all these derivatives are 0, and everything is good, right? So that kind of thing will force the snake to collapse, right? And you saw that in the example with the circle. So the problem with the basic snake, which comes from the way that we defined this external energy, is that the contour never kind of sees strong edges that are far away. So that's not good. And actually, let me just say there are multiple problems. The other problem that you could imagine is that, if I have any noise in the image at all, that will create, many kind of small gradients. And then the snake kind of gets hung up on those. Right? So we need to find a way to fix these problems, okay? One idea that you could do, which is something that does work a little bit, is you can imagine that I could blur the image and then try running the snake, right? And hopefully that would do a better job. And so in the interest of time, I'm not going to do that. You can do the experiment yourself, but you can show that life works a little bit better if I blur the image. What that means is that instead of having hard gradients only in one place, I have kind of like, so say this is my hard edge. If I make this softer, that means that I'm going to kind of spread out the gradients in a wider band around that hard edge. And that depends on, for example, the variance of like a Gaussian blur that I would use. And then I can attract the snake a little bit more further away than it was before, right? But still not going to be good enough in a case like this where the initial boundary is far away and I need to kind of pull in from a distance, okay? So the solution to this, which is pretty slick, is what's called gradient vector flow, okay? So the solution to this problem, or it doesn't fully solve it, but this mitigates the problem, let's just say, is called gradient vector flow. Sometimes you see that called GVF. Okay. So the idea here is that instead of using exactly the image gradient, we instead make kind of a new gradient field that is non-zero everywhere. So even in flat region of the image, it's going to be pulling the snake inwards to gradients that are strong further inwards, right? So the idea is that instead of using exactly the image gradient, we create a new vector field over the image plane. So let's call it v of xy. So there's an x component and there's a y component. And let's call E the edge map of the image, which is kind of like, you know, the magnitude of the gradient. Okay, so now what I want to do is I want to define this new V that is equal to gradient stuff where there is a gradient, and outside the gradient is kind of pulling inwards, right? So let me start on a new piece of paper. So V is defined to minimize. Now we got double integral. All right, so let me write this down first, and then I will explain what it means. I heard a sigh from the audience. It's not that bad. Gradients. Okay. So let me give you a minute to write this down. So let's unpack this for a second, right? This basically is saying that here, this is basically the magnitude of the edge map, right? How much gradient action is there, okay? And this is basically saying how similar is the thing that I'm creating to the thing that I want, okay? So what this is saying is that when I'm in a really edgy region, then the V that I create just kind of agrees with what's going on with the edges, right? So the high priority is when this is big, then this has to be small, which means I have to push, you know, V to be similar to the E in the right, you know, in the places where there are edges. This here is basically saying, okay, well, suppose that this number is small, then this term takes over. This is what I would say is the smoothness of V. So this is like saying that, okay, suppose this part doesn't matter, then this part is basically trying to make the V that I create very nice and smoothly, right? Whereas if I just looked at the edge map, there would be like this kind of sharp step between where I am locally and then far, far away, I step down to 0, right? So what I want to do is I want to kind of smooth that transition out so that even far away from the edge, I have like this nice kind of smooth transition towards the edge. And I'll show you an example of this that will make this a little bit more clear. And this here is kind of like a tuning parameter that kind of trades off how smooth the vector field is versus how close it is to the edges. So let me just kind of, again, recap what I just said. The intuition is that if this is big, that means that the gradient is large, and then the V is going to follow this edge gradient faithfully. If this is small, then the gradient is small. And then V is just going to kind of follow along to be as smooth as possible. And then this mu trades off kind of how smooth I am versus how faithful I am. Just like in real life. Okay, so this works a lot better than the previous case, since now the strong image edges are going to kind of diffuse out to the rest of the image. So let me just show an example of that to make it clear what we're talking about here. So I'm going to go back to my MATLAB. And again, if you look in file exchange for gradient vector flow, or GVF, you're going to find a package that was written actually by one of our RPI alumni, Chuan Wang. And so let me just show you what we get here. So I just kind of wrote a little wrapper around these functions. I think that I just called it my snake. I guess I commented a bunch of stuff out. Well, let's see here. I thought I had a function, yeah, snake hand. Okay, so it's thinking. Oh, okay, this is not what I want, sorry. Well, let's see what happens here. I think this is still not quite what I want. Okay, this is not what I want. Actually, this is getting better, but you can see that something is wrong. This is someone else's implementation of the gradient vector flow, and I can see this isn't working actually because if I zoom in, it has a little bit of what I want in the sense that you can see that now there are gradient vectors everywhere, but for some reason this implementation is not good because the 0 points of this thing are like not along the boundaries of my hand. Okay, so forget I showed you this, and let me stop this crazy thing. So what was my thing? Let's try, I have a function called hand GVF. Oh, okay. Better. Okay, so what do we have now? This is the same thing I had before, and if I zoom in on my hand, I can see that actually, you know, there are little vectors that are pushing the gradient from these places that would normally have basically 0 gradient towards the edge, right? So I've kind of diffused the influence of this edge outwards, and so you can see that this is going to pull the curve. Basically, the little arrow says which way is the curve going to go if it's sitting here, okay? And I can try to make this a little bit more clear. I believe that I made a version of this that makes the arrows a little bit bigger. Right, so here you can kind of really see that, again, a little bit confusing, but if we zoom in, like there are big arrows pointing from the outside in, and then big arrows pointing from the inside out. That's basically going to say that I'm going to push my curve inwards or outwards depending on where things are at. And so now let's try seeing how this works. So this guy is built into MATLAB in this image segmenter. So if you go to image segmenter, and I load up this image. So let's, again, draw my initial curve. Whoops. I guess in MATLAB I have to hold down the button. Okay. So now I'm going to go into active contours, say edge-based, and evolve this. Nope, this is way too many. Let's see if this works. Okay. Things are shrinking. And I can see that even though the curve started far away from the edges of my hand, it is slowly being pulled in to my fingers, right? And here I'm about halfway through, so it has more to go. But when it gets to the edges of my fingers, it's going to pull in and stop, right? Now here you can see actually, again, this curve is kind of dumb, right? It doesn't know that it's looking for my hand, for example. And so here you can see on my sleeve, it's caught by the edges that are on the little patterns on my sleeve, right? So if it encounters a strong edge on the way to, you know, what we would consider to be the hand, it's going to get caught up, right? So certainly if this hand was on a, you know, checkerboard tablecloth, then things would go wrong. And in fact, I'm not sure whether this will fail, but let's just see. I had a different version of this image that I took on like a wood grain. So a couple things that you should know about this. So one thing is that there is a, kind of a time penalty for bigger images, right? Oh, okay, so let's try what happens here. Let's try again. It's going to complain because this is grayscale. So let me just try hand. Again, there's no reason why this stuff wouldn't work on color images. It's just that the implementation doesn't always accept it. Oh, forgot to imread. Sorry. Okay, so this image is actually pretty big, 1224 by 1632. And so I'm actually going to resize this image to be quite a bit smaller just for the purposes of demonstration. Now it's 306 by 408. So now let's see if I can run this example here. No, not you. Image segmenter. I guess I still have one of these open. All right, so let's try loading. Oops, I guess I have this in my workspace. Yes. Him. All right, so now I have this wood grain image, and I'm curious to know how well this will work. I don't really know, but I assume that things are not going to work so well. Active contours, edge-based. All right, let's see what happens. See here, I feel like things are, not like totally going in the right direction. Like, for example, things that are, I think that what's going to happen is that, here, since the wood grain of the table is kind of like perpendicular to the contour, it's okay. The contour is getting sucked in along those relatively constant intensity lines. But here I think we're going to have problems where basically, since there are strong edges in the table, the gradient vector flow is going to just get caught on those edges, and it's going to have a hard time just jumping over the hump, right? So I think even if we were to let this go for longer and longer, we would have, not such great success, okay? So, the gradient vector flow is not like a silver bullet, but it works a lot better than just like regular edges, okay? All right, so there are two more things I want to talk about. Before I do that, let me just stop and ask if there are any questions or comments. Oh, multiple questions. Okay, question number one.
So I'm not sure if it's just because this is like a graphical display, but this method seems really slow. Do you know by any chance what the complexity is?
So method seems slow, and that's true. So I don't know what the complexity is off the top of my head. It certainly depends on the number of points that I have, and also it depends on, whenever you do numerical optimization, there's this kind of notion of like step size, right? So when I take a step along the gradient, how big should that step be? And so I think that what you can see here is that, first of all, the number of points around the contour is probably pretty high because this is a pretty fine detailed contour, so it's solving a relatively large system. And number two, it's chewing in only a very few pixels, if that, at every iteration, right? So it's going to take me a long time to get to the answer. So some of it depends on number of points, some of it depends on number of steps, right, or size of the step. But it is slow. I mean, it's not going to be like a snap your fingers and zip thing, how it goes. So something like graph cuts, for example, is much faster. You saw that I was able to do graph cuts at interactive rates last lecture, right? So this is definitely anything where you have kind of like this discretization of a continuous time, like partial differential equation, is inevitably going to be a little bit slower, for sure. And if you wanted to, I mean, I'm not even sure whether or not, like if I look in the MATLAB help, I'm kind of wondering, I think it's called active contour. I'm wondering whether there's even like any sort of a graphical, like if you have a GPU, will it go any faster? No, I don't think so. So yeah, I mean, yes, it can be slow. Other question?
Without a GI, are there common ways, or would you want to, without a GI, initialize the contours with some other properties of the image?
Right, so how would you initialize the contour, right? Yeah. So that's a little bit tricky, right? So I mean, definitely most active contour stuff assumes that you get that initial contour from somewhere, right? Now, you could be very crude about it. You could just say, okay, I'm going to draw a, so one example, right? You go, okay, I'm going to threshold the image very aggressively. I'm going to get the centroid of those points. So say I'm looking for a bright object on a dark background. I could find the center of that bright object, and then I could draw a circle whose radius is the width of that threshold thing times some factor, and then I let that circle contract until it snaps around the object, right? So you could do something semi-automated like that, but a lot of times when people talk about snakes, the contour is the initial contour is assumed to come from somewhere, right? And it may not necessarily be automatic, it could be human generated. But yeah, that's tricky, right? To figure out obviously if you wanted to put this into a fully automated system, you don't want to have some person who's, clicking on stuff, right? You could imagine that, for example, so I did a lot of work with medical imaging long ago, and so there are rooms full of, interns and radiologists who are basically, looking at CT scans and having to very precisely outline things, right? So you can imagine that it would be much easier on them if all they had to do was kind of like drag a bounding box around the object and then have this thing snap to it and drag another bounding box, as opposed to having to click manually around the contour, right? So it's not that unreasonable to think that there's some human in the loop when you're doing this. But that's a good question. Yeah.
And one more, could you go the other way to start from inside the
Yes.
object?
Could you go inside the object and expand out? The answer is yes, and that's something that's called the balloon force. And so I'm not going to talk about that today, but yes, there are ways to do that. And I guess I was a little bit breezy about, again, all the details, right? So for example, when I first showed you that circle example, the black circle on the white background, I tried a bunch of stuff, right? What if it's totally outside the curve? What if it's totally inside the curve? What if it's overlapping the curve? In those cases, you need something that will pull from inside as well as out and kind of force the snake to blow up. So I don't want to do that right now because I'm not sure whether it will work in any of my examples. But yes, there are considerations for making sure the snake expands outwards from places where it starts inside the contour. Yeah. Other questions or comments? Okay, so there is kind of one more cool idea that I want to introduce to you that makes life a little bit easier. So let's recall the first example that I did, which was I had the choice here, edge-based or region-based, right? So let's try this region-based thing. Whatever this region-based thing is, it seems like it's doing better and faster, right? So that's good. Although in this case, it seems like it's also kind of chewing into my hand, which is not great. But let's observe a couple things, right? First of all, this is, regardless of how good the segmentation is, it's also like picking up this other stuff here, right? Like it's picking up the little figures on my sleeve that are disconnected from the hand, right? And so clearly, this thing is not necessarily evolving a closed curve. It's evolving, there are like multiple closed curves here. There's the one around my hand. There's the one around these guys. There's the one around these guys, right? So what's happening there? So it turns out that there are a lot of segmentation problems. So, for all the stuff I just talked about, let me just say that snakes are generally, as I define them, a huge pain to work with, right? Partially because you are explicitly defining the contour of the object by a closed curve, right? And you have to keep track of like, where are the points on this curve, and do I have enough points, and so on. And so let's just say that snakes defined as a set of points around a contour I'm not going to sugarcoat it. They can be a pain. When snakes were first introduced, like people were like, oh, this is pretty cool. And so, for a while there was a lot of work on these kinds of contour-based things. And then it was observed, but there are some problems, right? Part of it is that, keeping track of the number of points around the contour, kind of the point distribution around the contour is a pain. It can be tough to get the points to kind of probe into concave areas, right? So you kind of saw that, in the case of my hand, the thing that took the longest time was pushing the contour into the narrow places between my fingers, right? The outside part was fine, but getting in those nooks and crannies took some effort, right? And that can be a pain when you're forced to distribute the points evenly around the contour, and some of these points have to really probe inwards to these places, right? They could bunch up in the wrong places, stuff like that. The other thing is that a snake, as defined, can never wrap around multiple objects at once. Right? So, for example, suppose that I was a biologist and I wanted to segment a bunch of cells on a plate, all of which had basically the same intensity to, foreground to background difference, right? Seems like I should be able to do this, but I don't want to have to, number one, either I'd have to initialize a bunch of contours and let each of these, shrink down by themselves, which could be a pain. I have to figure out how many of these do I need. If I use a single snake, the best that I could hope for would probably be something that would snap around the outer boundary of the objects without, there's no way that it could get these objects to be separated. And also, a snake can't do holes, right? So suppose that I had an object like a donut that had a hole inside, right? I could segment this with a snake and I get the outside, but I wouldn't be able to get the inner boundary, which may be something that I care about, right? So say it's like some sort of a machine part, okay? So to solve these problems, namely, so it's definitely the one about keeping track of all this stuff, and also, it's nice to be able to segment multiple objects and objects with holes and have like a single thing that will do all that at once for you, right? The solution is what's called a level set approach. And this is a pretty slick idea. So, and I would say that fundamentally, if you're doing snake active contour type stuff now, you're going to be doing it with level sets, not with the things I showed you earlier, right? So the idea is that instead of parametrizing the curve by a set of ordered points, what I do is I discretize the whole image plane. So I've got these xy coordinates, and I define what's called a level set function phi. Okay? And so instead of evolving a curve, I'm evolving this function over the plane. So evolve this entire function. And then the key idea is that the pixels where this function equals 0 implicitly define the object that we care about. Which could have, multiple objects, could have holes, and so on. So let me kind of do a better job of sketching this for you. So the idea here is that the curve that I get at the end of the day is the set of places where this level set function equals 0. So, for example, let's suppose that I have, this function of x and y. Okay, so this basically, anywhere that I have x and y, I can define this function, right? And if I set this function equals 0, that means that I have x squared plus y, that means I'm implicitly getting this circle of radius r, right? So to draw it a different way, this is kind of like saying that this function over the xy plane looks like, you know, some shape like this. And if I look at where this shape intersects, this is like saying, I look at this axis here, this is like saying that this point here is like z equals 0. And I look and see, what do I get in the xy plane? I get the outline of this thing, right? And so, in a way, I can imagine that I have a function that has like, you know, a shape like this, and when I intersect it, I could get this and this. Or I could have a shape that looks like this, and when I intersect it, I could get like a shape that has a hole in it, right? And multiple shapes. So this is kind of a slick idea, because as I evolve this function, actually the function can be changing all the time, and I can actually change the topology of what it is I'm finding on the fly. So instead of saying, oh, all of a sudden I discovered I have 2 objects instead of 1 object, I'd have to go back and change my snake stuff entirely. Here, the function just changes, and I just discover what my objects are, right? Which is kind of neat. And so a good choice for this phi is what's called the sign distance function. So, for example, all I'm saying is that, you know, in the xy plane, this is like saying that places on the curve have a value of exactly 0. Places that are inside the curve have a negative value. Places that are outside the curve have a positive value. And I can kind of think about this like a kind of an image. And so let me make this a little more concrete in MATLAB, right? So I made a little example, as I want to do. So here I have a object that has a complicated boundary, right? It's got the outside of the R, and it's got a hole, right? And so here, is a little demo I made that shows that on the left I have a 3D function you can see is this colored thing, right? And it's a function of x and y, and when I intersect this with my z equals 0 plane, it hits the curve in, whoops, I guess I'm upside down. It hits the curve in exactly the places that trace out the R. And as I change the level of the function, it hits this, you know, as I change the level of the plane, for example, I could say, okay, where is this function equal to 20? I get kind of the outside of the R. And then as I move this down, I can start getting the hole. And as I move it down even further, I get, you know, disconnected pieces, and then I get nothing, right? So this is the idea, is that this one function can encapsulate, come back. This one function basically encapsulates the shape of the R with a single function of x and y, right, which is pretty slick. And so the idea is that instead of, you know, evolving this complicated R contour, instead I'm going to evolve the colored function here and look at the cross-section of it at z equals 0 over time, right? So that's the idea. And so the basically idea is that evolving this level set function is kind of mathematically better behaved, let's just say. Right? So now I'm basically going to have a function x, y, t, and again, I'm going to, at every step of t, try and make this function a little bit better, right? Although I will say that, you know, there are many picky details to make this work, and I can't talk about them in 5 minutes. So, but this is the idea, is that this kind of school of thought came from fluid dynamics, actually. So if any of you are like Meckies, this is kind of like a fluid dynamics idea of how do I evolve the front of a changing, like how do I evolve a wave front, right? But this works pretty well. And then at the end, I use what I would call like an isosurface algorithm to extract, the final segmentation. So again, like if any of you have taken like computer graphics or something like that, you maybe came across this thing, and there are lots of functions to say, okay, find the place where this function equals 0, right? Marching cubes is an example of such an algorithm, okay? And this even goes to 3D, right? So you can imagine that if I wanted to segment the surface of a 3D object, then I go up one more dimension, right? So then I have a function of 3D space, and the place where I have that 3D function equals 0 will outline a cool 2D surface, right? So there are these one level up ways to do level sets. So let me just say that everything I talked about with respect to snakes can be done with level sets. I can kind of use the same types of internal and external forces, except that everything is done on this one dimension up function instead of on the image plane, okay? So I'm not going to go into the details of that. You can, again, look in Gonzalez and Woods for some more of the nitty-gritty. But this is a kind of a cool thing, and this is what MATLAB will do in terms of trying to evolve a function, I think. If you watch what those contours are, a lot of times they're not actually a single closed contour. So let me pause and ask any questions about this. One more thing I have to say. Last thing I have to say is that, final comment is that everything we've talked about today so far has been what I would call edge-based, right? Which, kind of stands to reason. We've talked a lot about edges and stuff so far in this class. But, what if there aren't really strong edges? So in the absence of edges, or at the absence, this is not the way you spell absence, absence of strong edges, we can use a region-based formulation. And actually, this will even work when I have strong edges too. The idea here is that instead of trying to push the curve onto the edges of an object, I could just generally say that I want a curve that separates the image plane into an inside and an outside. And this is my curve, right? And then the energy of my curve could be defined as something like I have some number that says over the pixels on the inside, I want the standard deviation of those pixels to be small. And around the outside, I want the standard deviation of those pixels to be small. So this is kind of like, this is like the external part. And then I could have something that says, also, I want the curve to be short, or, this is like kind of an internal force. And then I could have another term that basically encourages the curve to shrink, right? This is called the Chan Vese, or Chan Vese, I'm not sure how to pronounce it. Right? So the nice thing about this is that it doesn't force the image to have strong edges. You can imagine that I have an image that is kind of fuzzy, and it would still work pretty well. And so if you go to MATLAB's image segmenter and you ask for region-based, as we did here, that's what's going on here. So if you look here, it says region-based active contour developed by Chan Vese. So that's what's happening. And just as a final thing before we go, let's just see how we do with more complicated images. So like here, see how well this is going to work. So here's a case where I've got a really complicated interior and a blurry exterior. So let's see how we do here. So this is the region-based algorithm. Oh, no. So it's kind of coming around the boundaries of some of these objects, but then it's also somehow flipping out on the outer boundary. So maybe not so great here. Unfortunately, the way that this, the way that this image segmenter is designed, you don't really have a lot of direct access to the underlying parameters. So I think, honestly, you could probably get this kind of thing to work, but given the timing, let's just see freehand if this works. So here's another example where even though the zebra is really stripy, I wonder whether the region-based algorithm will work on this. Yeah, this looks like it's going okay, right? So you can imagine that fundamentally the interior distribution of the zebra is black and white, and the exterior distribution is green. And even though there's lots and lots of edges all over the place here, this region-based algorithm is still able to do pretty well because it's trying to basically maximize the difference in the distributions between what's inside the curve and what's outside the curve. And as long as there's green grass inside the curve, it's advantageous for the algorithm to push those pixels on the other side because that matches more with the outer distribution. So you can actually see that this works pretty well. So I'm glad that this example seemed to go okay. At this point, I could say I'm happy with the segmentation. Of course, it's still taking a while to dig into the interior legs of the zebra, but externally, things look pretty good. Okay, so any last questions or comments? All right, that's it. So thanks for listening, and